In this video, we're going to look at a modified form of two problems that definitely live up to the billing of multivariable calculus challenge problems. These will be our most challenging problems yet. Problems 102 and 103 from section 11.1 of Rogawski and Adams calculus book. Modified, actually part A is 102, part B is 103, and part C is an extra part that I added. And part C is where we're going to look at a Mathematica demonstration to help us understand what's going on here. And we'll do that at the end. So we've got kind of your standard parameterization of an ellipse. C of t equals a cos t, comma b sine t. In other words, this is the x coordinate, and this is the y coordinate. And before we go on, maybe the first thing we should see is that this does parameterize an ellipse. It does satisfy the equation of an ellipse when the ellipse is in the standard form, centered at the origin, and not rotated. Its semi-major axis is parallel to the x-axis. Its semi-minor axis is parallel to the y-axis, at least in this picture when a is bigger than b. And the equation it's got to satisfy is x over a squared plus y over b squared equals 1 for all t, no matter what t is that will happen. We can implicitly assume here a and b are positive. Go ahead and replace x with a cos t. Replace y with b sine t, and yes, this is set up to work. The a's cancel, the b's cancel, leaving you with cos squared t plus sine squared t, which is always equal to 1 no matter what t is for all t. So this does satisfy this equation of an ellipse in standard form like this. Okay, so that's your simplest parameterization for an ellipse. But we should realize that t, which you can often imagine as time, just for the sake of convenience, is not the same as the angle, theta, that's in this picture. It's not an angular parameter, unless a happens to equal b, and the ellipse is a circle. However, t does have a geometric interpretation. That's part of the point here. Part A says that t is going to be 2 over little a times little b times capital A, where capital A is the area of this region that's lightly shaded down here in pink. A is the area of the shaded region in this figure below. Okay, so it's a little bit strange, but we will see that that happens. And what that ends up meaning is with this particular parameterization, as the point moves with that motion defined by these equations, we get sort of equal areas swept out in equal times. Now that might sound like Kepler's laws, if you know about Kepler's laws from astronomy. It's not quite exactly the same, because with Kepler's laws, when you've got a planet moving around the sun is actually not at the center of the ellipse, it's actually at a focus of the ellipse, which is different than the center of the ellipse. So it's somewhat similar to Kepler's laws, but not exactly the same. In part B, we're going to show that there is an angular parameterization with this angle theta that you can come up with. Show that the parameterization of the ellipse by angle theta is given by these equations, right there, which, if you want, for the purposes of just visualizing things on Mathematica, you could think of theta as being time as well there. And in part C, when we use Mathematica, we will imagine both parameters to be time, whether we use a t or a theta. And in both situations, we'll find and graph the speed and distance traveled, or arc length functions, and compare those graphs and discuss what we see and think about why it makes sense. But that comes at the end. All right, so let's go on to doing part A. So what should we do here? We want to verify that t is given by this quantity right here, where again a is the area of the region that's shaded. Let's break this area down into two pieces, a1 and a2, and therefore the total area is going to be a1 plus a2. And let's go ahead and find those areas now. A1 is the area of a triangle. Maybe we can use 1/2 base times height. But what is the base and what is the height? We want to get those in terms of t. We want to use this parameterization. That's part of the point. Well, the base is the x coordinate, which is a cos t. that's the base of that triangle, times the height is y, b sine t. I am doing this derivation assuming that the point is in the first quadrant. You might wonder what happens if the point is in the third or fourth quadrant. How do things get modified? Does the derivation still work? We're not going to worry about that. Okay. We will go ahead and derive it assuming the picture is what's going on. We are in the first quadrant. And we'll see when we look at the graphs in part C that it is consistent for other quadrants. So that's A1, 1/2 base times height. What about A2? We need to add that. We need to find the area under this graph. Under a graph, I could probably do an integral to help me do that. Now you actually can do the integral based on the parameterization. There is a way to do that, but most people don't know how to do that. So instead, I will use the integral as you should know by now from your first couple semesters of calculus. I will do the integral of this function of x, whose graph is the upper ellipse here. So I need to take the equation of the ellipse right there and solve for y as a function of x. And if I want it to be the upper part, then I better take the positive square root. So I'll do it all in one step here. Although there's a number of sub-steps, I'd want to subtract x over a squared from both sides, get it on the right side. I'd want to take the square root, positive square root, to get rid of the square there, and then multiply both sides by b. Y would be b times the positive square root of 1 minus x over a quantity squared. That b, being positive, like I mentioned earlier, could be thought of as square root of b squared. And I could combine the square roots. I could write this as y equals square root of b squared minus b squared over a squared times x squared. Okay, that's one way to write it. So I need to integrate that function from this value of x to this value of x. Integral square root b squared minus b squared over a squared times x squared. The right limit is a. What's the left limit right there? Well, get it in terms of t. We want to relate these things to t. As we saw before, it's the same as this distance right there. It's a cos t. That is going to be the lower limit of this integral. Kind of strange, but that's the way it is. So this, if I can simplify this somehow, maybe I can see that this equation is true. It looks unlikely because it's so complicated looking, but if you don't make a mistake, it actually does work out. Let's see how that works out. So we got to do this integral. That's a pretty complicated looking integral. You can do it with a substitution. You can also use your technology. A program like Mathematica could help you do it. You also could look things up in a table. You can do this with a substitution, and it turns out the best substitution to do is to let x equal a cosine of some quantity, use something other than t. How about the Greek version of t, which is tau? Let x equal a cos tau. This turns out to be the best substitution to make. Dx is going to be then negative a sine tau d tau. I can also say that tau is the inverse cosine of x over a. You could also call that the arc cosine of x over a. And if I'm going to do this as a definite integral like this, I'm going to need to change the limits of integration, at least if I don't want to just find the antiderivative first. But I'd like to keep it as a definite integral the whole way. Don't forget about this part. Let me combine it as ab over 2 cos t sine t. Okay, so what's going to happen with this integral? So I'm going to get the integral, replace x with a cos tau. I'm going to skip maybe an algebra step or two here. Think about that. I'd get an a squared cos squared tau. The a squared would cancel with this a squared. And I'd be left the square root of b squared minus b squared cos squared tau. I can factor out a b squared. So I did a few steps there. dx is negative a sine tau d tau. But I need to change my limits of integration if I'm going to say these are equal. So be careful here. Let's see. The lower limit here is x equals a cos t. That is a t there instead of a tau. Imagine making the replacement here. Replace x with a cos t. The a's will cancel, giving you arc cosine of t. Arc cosine or inverse cosine is the inverse function of the cosine function, and you are going to get t back when you do that. Okay, at least if t is in a certain range of values. Technically speaking, the arc cosine function always gives you outputs between 0 and pi. We would be assuming that if we are in the upper half of the ellipse here. The lower limit of integration becomes t. How about the upper limit, a? When you replace x with a, you get a over a. Arc cosine of 1, or inverse cosine of 1, that's 0. Okay, now it's a little strange. In the picture, t is bigger than 0. How do you deal with that? Well, you've got a negative sign there. You just flip the limits of integration around and get rid of the negative sign. ab over 2 cos t sine t plus the integral from 0 to t. What else will happen? And again, that negative sign is going to go away. This is the same as sine squared tau. Square root of b squared is b. B is positive. We can bring the a in front here as well. Square root of sine squared tau technically is the absolute value of sine tau. Technically, again, we're in this first quadrant here. I could assume sine of tau is positive and not worry about the absolute value sign. I'd have sine tau times another sine tau is sine squared tau. Again, we're not worrying about what happens if we're in some other quadrant. Let's just see what we get when we assume we're in the first quadrant and see at the end that things are consistent. So it's not really a proof here that we're doing, not a full justification. So how do you do this integral? You could look that up. My favorite way of doing it is to use a trig identity to replace sine squared tau with 1/2 minus 1/2 cosine of 2 tau. Integrating that would be easy. Getting close to the end here of part A. Okay, so integrate AB times 1/2, AB over 2. You get AB over 2 times tau, evaluated from 0 to t. That's just going to be AB over 2 times t. Which, this looks promising when you compare it with this. Remember, all this is equal to capital A here, right there. What about integrating this? You're going to get minus 1/4 sine 2 tau. Tau going from 0 to t. And that, in the end, I forgot my AB, A times B. That, in the end, is going to give you AB over 4 sine 2t, since sine of 0 is 0. And there's a trig identity, a double angle formula that says sine 2t is 2 cos t sine t. The 2 will cancel with the 4 to leave you with the 2 there. So we have AB over 2 times cos t times sine t, and there's a minus sign there. It does completely cancel with that, leaving us in the end with AB over 2 times t. Now we can just solve that equation for t. Multiply both sides by 2 over little a times little b, and I get the answer for part A. Okay? All right, pretty challenging. It's doable, though, if you're real careful about concepts. What about part B? What if we're thinking in terms of this angular parameter, theta? Why is this the parameterization of the ellipse based on that? All right, let's go ahead and look at the triangle there in this picture. If I label the hypotenuse of this right triangle, and it is a right triangle, H, I could call this side h cos theta and this side h sine theta, just using trigonometry there, SOHCAHTOA. Sine is opposite over hypotenuse and cosine is adjacent over hypotenuse, which would also mean the tangent of this angle is the same as the slope of that line. Rise over run. The slope of that line is rise over run is h sine theta divided by h cos theta. The h's cancel, leaving you with tangent theta. That's going to be the slope of that line, which means the equation of that line can be written in terms of theta as y equals tangent theta times x. Maybe you already knew that, okay? And if you did, you could have just written that down. That's the equation of that line in terms of theta. If I can figure out where it intersects the ellipse, based on the equation of the ellipse there, that's going to ultimately give me x and y in terms of theta. I hope that makes some sense. So what I'm going to do now is I'm going to take this equation and substitute it up into here in place of the y to get an equation involving only x, and a and b as well. Solve that equation for x in terms of theta, then use this equation again to get y in terms of theta. All right, so let's see, that algebra is a little bit nasty here. So let's see, let's go ahead and replace the y with tangent theta, or for that matter, replace y with sine theta over cosine theta, since that's where we're going toward. Maybe let's go ahead and do it that way. So I would go ahead and square things out. X squared over a squared. Replace y with sine theta over cos theta. I would get, and times x as well, sine squared theta x squared over b squared cos squared theta equals 1. I can factor an x squared out of these two terms. Also get a common denominator of a squared b squared cos squared theta in what's left. That means over here, I factored out an x squared, leaving me with a 1. To get this to be the denominator, I have to have a b squared cos squared theta there. And here, after I factor out an x squared, I have a sine squared. I already have b squared cos squared theta in the denominator, so I need to also get an a squared. I get a plus a squared sine squared theta. And this looks promising when you compare it with these things. I think you'll see. Because now I can just multiply both sides by the reciprocal of this and take the positive square root, say we're in the first quadrant here, where x is positive. And if you do that, you very quickly get to the final answer for x. AB cos theta divided by square root of b squared cos squared theta plus a squared sine squared theta. Okay, and that does match what is up here. AB cos theta over square root of, okay, I have it switched around on the bottom, but it is the same thing. Okay? What if x were negative? Well, then cosine of theta would be negative. This still ends up giving the same formula, the same answer. We would have been taking the negative square root down there, but the cosine would have been negative. You end up getting the same formula in the end. Actually, the cosine would have been negative. What about y? Just multiply x by tangent theta. Multiply it by sine theta over cos theta. The cos thetas cancel, leaving you with ab sine theta over square root of b squared cos squared theta plus a squared sine squared theta, just like you see up here, except with the things in the square root switched around. Okay, so that we have derived the answer to part B now. And now we'll go to the Mathematica to try to understand this stuff more intuitively. We'll think about both parameters in both parts A and B as being time, and try to understand the motion generated by these parametric equations. Okay, now we're on to part C of problems 102 and 103 of these two different parameterizations of ellipses, where we find the speed and distance traveled functions. Arc length function is another name for the distance traveled, and graph them and see some interesting things. And we're going to use Mathematica like we always do here, and it's going to be pretty complicated but really cool in the end, because we're going to realize something based on a graph that we see. Something unexpected happens with the angular parameterization in theta that I didn't expect, but I saw with these graphs. So that's supposed to be an impetus to try to learn more, explore why certain things happen. Once more, I re-emphasize you don't have to know Mathematica code, but maybe this is going to inspire you to want to get Mathematica, or at least a student version of it, so maybe you don't pay as much. Anyway, these functions right here enter the simpler parameterization. X equals a cos t, y equals b sine t. We've got the c is the ordered pair, x1 comma y1, and the velocity vector right there. And the second group is the second parameterization, more complicated formulas involving the parameter theta. This code right here makes the static picture. Again, don't worry about how complicated that looks. We see the static picture. I actually did make that more complicated than it had to be up here. The reason I did that was because I wanted to allow myself to use more complicated code to make the animations, and it was necessary to get the shading right. These functions that I'm entering here and here, ellipse graph and region graph, are new functions I'm going to create that allows the code down here to be more readable. Don't worry about the details. It's just allowing me to make the ellipse and make the shading and change those things as A and B change. Let's go ahead and enter this code to see the motions. Unfortunately, because contour plot and region plot are so computationally intensive, and in fact to make nice graphs you also have to do something else that makes more computationally intensive, performance goal error equals quality, it makes it a non-smooth motion, herky-jerky kind of, as you let time vary. Capital T here represents both t and theta. I'm thinking of both parameters as being represented by time, seeing the two different motions, but it's not real smooth. Sorry about that. But we can still see some details here. We see that the red graph, the red dot and the red line segment, is sweeping out equal areas in equal times, kind of as if it was following Kepler's laws, but it's again not exactly Kepler's laws because the sun is not at the center of the ellipse. It would be at a focus for real life suns and planets. But that motion with the red one is sweeping out equal areas in equal times. It's tough to tell that it is looking at the picture, but that is the case. And that does mean faster motion for the red one at the top and the bottom, and slower motion at the left and the right. The blue one is sweeping out equal angles in equal times. It's got a constant angular speed here. That's maybe a little easier to tell just by looking at it, but still a little tough since it's not real smooth. Okay, so they are two different motions. Let's also notice that when t is, so they start at the same point at the same time. When t is slightly positive, the blue one is ahead of the red one. But then the red one catches up, and they're at the same spot when time is pi over 2. Then the red one's ahead, then the blue one catches up, and they're at the same spot when time is pi, etc. They play this dance back and forth about which one's going faster and which one's going slower as far as the dots go. By the way, for both of them, the dots themselves are not staying at a constant speed, even for the blue one. Okay? The red one's sweeping out equal areas in equal times, the blue one's sweeping out equal angles in equal times. You can see this a little bit better as smoother motion if I get rid of the area shading, less computation. I also am letting a equal 4 and b equal 2. We see the ellipse for that. Notice the subscripts 4 and 2. Only capital T is going to change now. That does make for a smoother motion. You can see a little bit more clearly that the blue one is rotating at a constant angular speed. The red one, again, is definitely not. It's rotating faster at the top and the bottom. Look at the line segment there, and slower at the left and the right, but it is sweeping out equal areas in equal times, though again that's tough to see. By the way, with the previous animation I could have changed A and B as well, to make, for example, a more eccentric ellipse by making A bigger and maybe B smaller. And we can see the motion based on that as well. It's a little bit more extreme. In the smoother motion case, I can also include vectors. These arrows, these are velocity vectors. They are always tangent to the curve at the point that they are based at. And the length of the velocity vector is the speed, so you can see the blue one does start out with a longer velocity vector, so its speed is higher than the red one, so it moves ahead. But then the red one, the arrow gets longer for the red and it catches up. It's longer for the red still here, so the red is pulling away faster, but then the blue one has got to catch up, so its arrow becomes longer again, and they meet again at t equals pi. And the same kind of back and forth dance continues to happen as you go around the ellipse. And that's kind of neat too. All right, now we're on to the formulas. And here we really do need some sort of computer algebra system like Mathematica, especially for the distance traveled, arc lengths. The speed functions, what do their formulas look like? They're not too complicated. Here again is the simpler parameterization. X equals a cos t, y equals b sine t, and there is the speed. Think of a and b as fixed. That's a function of t, and it can be graphed as a function of t. Here is the speed for the more complicated parameterization involving the angle theta. It is more complicated looking, but still not terrible looking. In both cases, again, we're imagining these to be representing time, and therefore representing different motions as we already saw. Very basic principle is that when you integrate, if you want to find the distance traveled or arc length along a curve like this, you can integrate the speed. Well, you do need to also make sure the antiderivative that you're after has a graph that goes to the origin, so that the distance traveled at time 0 is 0. What is the integral for the simpler parameterization? It's kind of complicated, but not terrible. But wait a minute, what in the world is this? Elliptic E, what is that? You might go to the help menu here and look up elliptic E. What does Mathematica's documentation center say it is? It's my complete elliptic integral. What in the world is that? Well, it's a function you've never heard of before, in all likelihood. If all you've taken is, say, a couple semesters of calculus. You're used to other functions, polynomials, rational functions, which are ratios of polynomials, trig functions, cosines and sines, logarithms, exponentials, square roots, cube roots, and a finite number of sums, differences, products, and quotients, as well as compositions of those things. Elliptic E is a different beast altogether. It's a new function, a non-elementary function that most likely you've never heard of before, but the programmers of Mathematica have programmed elliptic E into Mathematica, and we can make use of this. This does evaluate to a value of 0 when you plug in t equals 0. Percent refers to the preceding output, and doing this will plug in t equals 0 into that. No matter what a and b are, the graph of this goes to the origin as it should. And we can copy and paste. I love copy and paste. Copy and paste this into this to get our distance traveled function for the simpler parameterization. Now onto the more complicated parameterization. We integrate the speed again to get the distance traveled. This formula is even more complicated. It even takes a few seconds to calculate it. There it is. Yikes. Very complicated. Also still involves elliptic E. Does this evaluate to 0 when theta is 0? It amazingly does, no matter what a and b are. Unfortunately, an extra complication comes up when we try to use this formula to do the second distance traveled function. Turns out that this formula only works when theta is between 0 and pi over 2. I don't want to go into why. And so in terms of copying and pasting it like I did here, I'm calling this dist2 first piece, and it turns out I have to use the which function in Mathematica to make a piecewise function that allows me to use this formula for all theta between 0 and 2 pi. I also needed a function I created called circumference here, related to the circumference of the ellipse, to help me do this. Don't worry about it. Here are the graphs. That's more important for us. And we're going to see again something surprising in this, the unexpected thing that happens, and this is the coolest part of this. What do we have here? So we have time as the horizontal axis. That's really capital T. We have A and B, the semi-major and semi-minor axes of the ellipse that we can change, and the graphs do change if we do make those changes. Do notice, okay, the dash graphs, if you think about it, they have to be the speeds. And the non-dash, the thick bold ones here, have to be the distances traveled. And do notice the distance traveled is the same at time 0, time pi over 2, time pi, 3 pi over 2, and time 2 pi, because those dots come back together at all those times. Also notice that for small values of time, the blue one is higher in speed than the red one. That was the blue dot was going faster than the red, which we saw in that animation. Again, the red one's the simpler parameterization, and the blue one's the more complicated one. Then the blue speed goes lower than the red. But the interesting thing that happens, which maybe you've already seen it here, is this little up and down right there, and also near 0 and 2 pi. What in the world is going on there? What that's illustrating is, for example, the speed of the blue one is actually not maximized at 0 or pi or 2 pi. It's maximized for values of time slightly less or higher than those things, which would be completely unexpected just looking at the picture. Just watching the animation, you would never expect that. So that's something surprising. It's something that should drive you to want to understand why more deeply. We can do that to some degree with Mathematica, but you might have to think about it symbolically, use skills that you develop here in the future to help you understand that more deeply. You can't really tell the ups and downs there with just the distance traveled. I mean, it is a little weird looking in here. It's evidently concave up and concave down. We're getting some inflection points happening more often than you might expect initially with just looking at that. Is there any way to intuitively tell why that's happening? Why is the speed not maximized at the right and left for the blue one? It is tough to tell, again, just looking at this. Let me just say, as a little hint, it's related to the fact that not only is the ellipse far away from the origin when you are close to 0 and pi, but also because when it's real eccentric like this, a real thin ellipse, the curve itself is moving toward the origin, not exactly toward the origin, but generally speaking in the general direction fairly rapidly for small changes in theta. That's another intuitive part of the reason why the maximum speed for the blue one is not at 0 and pi, but slightly higher and slightly lower than those values. But I'll let you think about this. I hope you've been inspired to try to learn this kind of stuff in more depth and maybe use Mathematica. It really is an amazing tool, and I hope you'll enjoy continuing to use it, see me use it in the future. By the way, one more quick thing. Norm calculates lengths of vectors, and these are velocity vectors, and we can see that these are actually speeds, and we get a maximum near 0.25 when a is 4 and b is 2. 4.3 is close to the maximum that we see right there. Okay? That's a final thing that I'll show you. We'll see you in the next video.